Hello ladies and gentlemen, welcome to another video on this channel concerning the Minuteman machine and the ultimate quest of 3D printing a Banshee in less than a minute. This is the Minuteman machine, a 3D printer that is totally useless in day-to-day applications, but certainly pushes the limits of physics and 3D printing throughout all its unique components. One of the most striking things is its very unique hot end. As you can see, it features 4 filament inlets that lead through a massive copper block into a single nozzle. So today I want to bring this technology right to your printer. Have a look at here. What looks like a total mess, and it surely is one of the second-gen prototypes of pretty much the same thing that is happening here. We're chilling at 215 degrees and we're going to do an extrusion move at 150 cubic millimeters a second. As you can see, we're feeding in 4 filaments, 2 different colors, both PLA at that point, and what we're getting is a steady stream of thoroughly melted material. And if you're having a real close look here, you can see it is extruding 2 colors at once. So join me on my today's quest of figuring out all the stuff you need to build a hot end like this, that is not only capable of producing that kind of flow, but is also easy to operate, light, so applicable for Co-XY system or something. As always, I'm gonna make all my findings here transparent, and at the end of this I will give away free plans to build this on your own. So stick with me. My name is Jan, I build stuff so you don't have to.
Da 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 da.
As a really short explanation, this is a very typical extruder and hot end setup that has been on the market since, I don't know, for the last decade. And while there has been a lot of innovation in this field, pretty much all of them use the same techniques. So at the very start you got some kind of a feeding mechanism that feeds raw filament into the stream. This is called the extruder. Then you either have a Bowden tube of a certain length in between, or have this as a direct drive setup. So these are coupled butt to butt. Next up in line is the so-called cold end. We need to control in which way the filament is heated, and this is the part where it should stay absolutely cool. And that's why this heat break comes in next. This screws in here. Back in the day this was just a stainless steel part for its low heat transfer. Nowadays we build them from copper and titanium. But what it essentially does is builds a heat break from the cold side to the hot side. This will get screwed into here, and as you can see you got a thermistor and a heat cartridge inserted in here that is being controlled with a PID loop to keep this hot end at a set temperature. And after passing through this heat block it will exit through the nozzle, which gives it its final shape and diameter and whatnot. The amount of filament we can melt in a given amount of time is specified basically by the heat transfer of the used material. This is aluminum. Nowadays the high-performing hot ends are built from copper. To increase melting capacity we can either go way up in temperature, which is not always an option, or make this heat zone longer. But you can't make it infinite long because you lose all the control over your puddle of filament that is exiting. You can't do basic retracts, etc. So another way you can tackle this problem is by using more filament strands at the same time. So what basically happens if you have a given amount of hot end length and feed 4 filaments in at the same time, you basically quadruple the time the filament passes through the heat block for the same amount of material that is exiting. So this is one of the complete assemblies I have on there. I'm really happy with the results. I took a peek in there. And then we'll go into all the nitty-gritty details about how we can place our melting channels, how these channels have got to be in terms of their geometries and surface roughness. Then we'll experiment with different materials we can use. And then finally talk about how we're going to heat this thing up. I'm going to show you all the CAD drawings, all the data I collect through all these tests. And then in the next video we're going to use one of these hot ends in an improved version and put it on a very unique printer, which is not the Minuteman machine, by the way. So what makes this approach really unique is the fact that all of these parts are SLM printed from aluminum for now. This gives me a total freedom of design. I can do whatever I want in the internal geometries without having to go with an end mill or something. And I just have to do some very basic rework to make them fit together and just work. The other big advantage is that you are pretty much able to just download the Hotend as a step or STL file or whatever. And then there are certain services out there where you can upload parts and just have them SLM printed and shipped to your place. One of them, which happens to be our today's video sponsor, is PCBWay. And I can show you just how easy it is to basically acquire parts like this. So you basically go on the PCBWay website, upload the step files into here, choose the right material, which is aluminum in this case, select the desired quantity, and you get an instant quote right away. They also offer services in sheet metal design and CNC milling, lathe work, PCB manufacturing, you basically name it. The quality of these parts I received were top notch and we're here in no time. So thank you again PCBWay for sponsoring that content, and let's dive straight into it. Alright, looking at my screen here, this is pretty much the Hotend you just saw extruding some material. And we're gonna go through all the components and have a look at what I've built here. Everything in the compartment here of cooling is just to have something here. We're gonna focus on all the mounting points and how to cool this and that. We're gonna focus on that on a later point. Let's go over the internals. So having a look at the cut section, you can see we got 4 inlets here. We're gonna go through the cold end section just with a 2mm diameter hole. This green cut part is the heat break situation, and this is the internal structure of one of those items. And I got 3 of these Hotend assemblies here in the test, which we already performed. These cut things here are for the heaters that are in here for now to heat this up. There are 3 components I want to test. So the first one has this tangent lines which are connecting the four filament strains. And then I got pretty much the same thing with a rather harsh bend in here to make that filament go down there. And then in the tangent one I got these 2 comparison here. The one, it's basically down here at the combining section. One of them has a 4mm outlet and one of them has a 2mm outlet. The thing I want to test here is how much influences that the back pressure of the system, because now we got 4 filament strains, so basically we do have a lot more volume to put through there. And with this kind of system we could use nozzles from 0.2. Basically, I tested that on my other Hotend to up to 2mm. But also, if we enlarge that, and a 4mm hole has the same area cut section wise as 4 times the 1.75 filament. So we could basically go up to a 4mm nozzle and not lose, we don't have to expand and slow down the material as it passes through the Hotend. And I've already tested that yesterday. And yeah, as you can see here, these are the results from 100 cubic millimeters to 200 for each of these 3 Hotend tests. This is the straight angle, this is the tangent angle in 4mm, and this is 2mm. And yeah, here are the results that are being weighed. So 1.26 grams is pretty much the nominal, and here I got the deviation from nominal. I don't really have tested this setup before. It is really performing quite well in terms of flow and pretty much matches my expectations when it's just from the calculation side. Aluminum with its heat transfer, etc. So that was working out way better than I thought, because with the SLM printed surface roughness I wasn't even sure if any material would come out of the nozzle, but it did behave as if it would have been a standard milled or drilled Hotend. And as you can see, this is the deviation here in the graphs in percent. So keep in mind this is just the -2 line. So everything above here could also just be a measuring error. All of these are pretty much performing the same way. We get the drop and where the extruder actually starts skipping. By the way, I'm just going with 0.75 amps on this tiny tiny extruder motor which is driving all 4 gears at the same time. So I could up the amperage and get a little bit more flow out of there, but we can basically derive where the limits of the melting capacity are beforehand, and we don't want to like use the system at 80-90% of its load all the time. We want to be more like in the 50-60% range. That is a very good working point. And visually you can see that right about like 150mm cubes of filament, there is a difference you can actually see in the filament that is coming out. So the viscosity is changing, and therefore I guess 150 is absolutely safe where we're right now, and if we want to push it we can go straight up to like 180. But this is all being done at just 215 degrees on a high flow PLA from Fiberlogy and a 0.8mm nozzle. So full disclosure here, so most of the manufacturers of hot ends will give you just the best case scenarios for their flow ratings. So we could go, and I did that yesterday, up to 250 degrees, and all of these hot ends will add 50 cubic millimeters of flow, so topping out at 220, 230 or something. But we want to have normal scenarios. We don't want to push material to the absolute limits and overcook it for certain regions where we don't ask of that volumetric flow and the filament stays longer in the heat zone. We don't want to have that. We'll also do testing on how these systems perform on like 0.4mm nozzles, etc. I think if we like stay at the 150 cubes or something, we may be able to even push that through such a smaller of an orifice. And most people that are using systems like this and demanding such high of a flow will have to use nozzles above 0.6mm orifice diameter, because then if you're just printing smallish benches, I've shown for the last half year that we're running into physical limits of cooling that down again. So we're talking mostly big prints, big and longer layer times. So I think 0.8 is a sweet spot for a system like this and should give us the most like valuable data. When testing yesterday, I also had a thermistor up here in the cold end section to monitor how much of that heat travels upwards into that area. Of course, we have to, especially with PLA, with its glass transition temperature somewhere above 50 degrees, we have to make sure that this here stays cool enough so the plastic isn't getting into somewhat fluid state. We lose all our control over that puddle at that moment and it will just clog up. Even when this hot end was at 250 degrees with a blower fan up here, we didn't exceed like 48, 49 degrees. So I think with a bit of tweaking we get that even a few degrees lower. Right now it is also 30 degrees here in the company. So I guess we can figure that out. And for the whole system, I know that it's working. I know how much of a flow we can get through here. So now let's do some different testing to see how much we could improve that in the next version. And I'm going to show you how we will do that. This is the other piece that you have seen laying around on the CMM. And what I will do here is test a single filament input and see how much the geometry of that channel will increase or decrease its melting capacity. Let's toggle the cut view. So the first two lanes are pretty much a reference or control test. So we want to have this first one just straight from the machine, SLM printed with surface roughness all over the place. The second one will be with the same basically, but drilled open with a 2mm reamer, so we get a nice surface finish and see what kind of a difference it makes. Is it even beneficial, as stated in one of my last videos concerning these hot ends, to have a rougher surface? We're going to test that now. Or do we want to have a completely polished thing and then we'll have to do all sorts of measures to achieve that? And the next one are labeled as flat and curve. So let's have a look at flat for a second. Basically, the whole thing about my initial hot end is that we have to get to the core of the filament. We want to have a thorough melt through all of our system. I achieved that on this hot end because we're splitting it right in the middle. There is a splitting geometry integrated in here, But to make this publicly available, we have to look at patents, and the splitting geometry is being patented by Bondtech/Slice Engineering, and we want to respect that, of course. But we have to talk about patents on this stuff later at some point in the video. I want to try different things to actually get to the core of the filament, and that is, for once, if you have a look at this cylindrical part here, what we're going to do here is like strip away the outside that is already being melted off the filament that is entering the heat zone. And this section here does have the same area cut section wise than the cylindrical 1.75 or 2 mm part up here. So we basically want to squish that and make it more wider but narrower the gap. If you can see that here in this setup. I'm interested to see what kind of a difference that makes here and if we can increase our melting capacity with this kind of setup. Basically, this is the last lane check. So basically, filament comes from above, and when it hits that first curve here, the same thing is happening. So we want to shear off the already melted material from the outside and expose the core while it's traveling down. And the same thing is also happening here on the other side. If this is promising, we could also make that 3D. So basically, all four sides of the filament are being stripped of their most outer layer. And as I said before, this will be done with a single setup. This is the part you're seeing in CAD. And we're going to use some old E30 V6 hardware to go from like lane to lane and check which one of those is the most potent in melting capacity. And then we want to integrate that into the existing one to even increase the, let's say, 170, 180 max flow at 215 degrees. Let's see if we can surpass 200 or even more. And we're set up here. So I just plugged in one of the tubes here, and then this is an E30 V6 clone, just adapted with the standard stainless steel heat break, and again the same 0.8 mm nozzle. And this is the straight section, basically straight how it came from the SLM machine. So we're just gonna see what our baseline is. This is 60 mm in length, plus 6 mm of nozzle stick out or something, and then let's say minus 6 mm from the heat break that it's been threaded in. So 60 mm in aluminum. My prediction is that we can run somewhere in the neighborhood of 45 to 50 cubic millimeters a second. That would make sense. Let's see where we're at. So I did some tests as a preparation, and I settled on I want to further investigate flow rates from 30 to 100 cubes. Let's see if we can reach that with some of these approaches. This is what my G-code looks like. So I'm flushing the hot end with the feed rate of 30 cubic millimeters in the first line. 300 millimeters of filament are going through, so I'm gonna stabilize everything. And then I'm gonna do one extrusion move that is extruding material that is worth 1.25 grams. I have a pause command every now and then, so I'm gonna do a flush, remove the material from the nozzle, then hit play again as fast as possible, and then I'm gonna pull off all the material that has been extruded in that move and just gonna weigh it on a precision scale. So it's raining pretty bad right now, so you may hear shit, so let's just go. This is the flush command. Right when it stops, I'm gonna pull it off, and this is like my specimen to put on the scale. Yeah, and it's right on money. So I've just passed 60 cubic millimeters a second. It is still able to melt all the requested material in a given time. But you can now see that there is some serious die swell going on. So I'm guessing the viscosity has changed. The material itself isn't fully melted. I mean, it's able to push it through this 0.8 millimeter nozzle, but there is no mechanism like a CHT or splitting geometry or something that really gets to the core, but it still manages to do that. That doesn't necessarily mean that it's good for a real-world 3D printing application, but I'm just gonna see how much of a graph I can derive from that. So this is again the flushing move. As you can see, this is bigger than 0.8. Resume, and this is extruding at the same, at 65 cubic millimeters a second. You can see the whole thing is a bit shaky now because it's putting a lot of stress on that Bowden tube up there. This is the end. And yeah, according to the scale, it still did extrude the requested amount, but you can see there is definitely something changing in viscosity. So let's move on and see how much I have to request before the extruder starts skipping. I could extrude material all the way to the end. There is just minor deviation to nominal, which could just be from compressing the filament. But have a look at this here. This is what material looks like at 35 cubic millimeters a second, and this is at 100. So this is clearly not the same. Even the scale says they're the same. But in a real world printing application, this material isn't coming out hot enough out of the nozzle. So I guess to draw better conclusions from this and make it comparable, I'm going to switch to a smaller nozzle, let's say 0.4 millimeters, and see if we can get like a sharpish line in the graph that tells us where extrusion forces are going through the roof in a very short matter of time. So this is looking more like the data I need. Last move was 80 cubic millimeters, let's do 85, and you'll see that this will go. Yeah, you can see the PTFE tube isn't even able to hold the... I'm gonna abort here. We got a mixture of skipped steps up here from the extruder, and then also the PTFE coupling isn't able to keep up. So it's a clear indication that our forces are too high here. And this is something we don't want to have when we do standard 3D printing. We want to stay in the range where the system is comfortable. So I'll put these on the screen later on, but you can see here I could measure the first deviation of 2% at around 60 cubes. Then it started to go down, and after 80, yeah, the system isn't capable to do that. So the thing is, take these numbers with a grain of salt. This isn't like comparable to any other 3D printer, Hotend or something. I just care into relative measurements here. So I wanna like put this hardware here to the next lane and see where like it differs. I want to draw a conclusion if it makes sense to really tackle the core, if we want to have the surface rough or drilled out or whatsoever. I hope we're gonna see something, because my like results where it starts to drop off are right about in the middle of my testing numbers. So let's see if the other lanes skip before or skip after that. And then we're going to integrate whatever flows best into our next iteration of Hotends. Let's do that. This is exactly what I wanted to see. So we got again skipping at kind of the same, maybe a bit earlier in the process. I managed 55 cubes without any problems, and then you could already see that the Hotend was struggling and forces downwards were quite high. But if you ask me, it skipped a step, let's say 5 cubic millimeters before the raw SLM one, and that is really good for various reasons. That means we can totally SLM print Hotend melting passages, lanes. That is a real big advantage for everyone that is not able to do it on a CNC and just want to test stuff. I mean, I've just done this one simple test, and there are a whole lot of other variables in terms of how to polish that, etc. But I will put in a clip of a few months ago where I built this Hotend for the Minuteman machine, and I was debating with myself if I should polish or sandblast the internal geometries, and I did go for sandblasting. And I'll put in here why I think this is the way to go for filament-based extrusion melting. I want to go ahead and bead blast that to give it a really rough surface finish. My theory behind this is the following. So let's imagine this PTFE tube of 4 millimeters is of filament strain. So without thinking too much of it, when the extruder pushes the filament into our heat zone, you basically think that the whole filament is traveling down that path as a whole. But I've seen this in many other applications, and my understanding behind it is the following, that it's actually not like that. What essentially happens is there is a heat transfer in the most outer zone of the filament, and then this filament is actually kind of like sticking to the walls, and then the inner core, which isn't really up to the temperature, because heat transfer in plastics is bad, is actually pretty much moving like this. So the walls stay, and the inner core, which isn't heated up yet, is traveling along its path or is being pushed by the extruder. So if your channel walls are being polished as fuck, then my understanding or my theory behind this is that this outer part doesn't really stick to the walls very good. It is kind of like doing a stick-slip effect down there. And what you end up with is a pretty chaotic movement of this whole strain. What I'm trying to find out is if we do intentionally rough up the surface, at least in the very upper part, can we have that outer part mostly being stationary up there and can have this pushed very controlled? Because the friction of this inside here can basically be described as fluid friction, while this isn't to the outer wall. So my theory is that this is being accountable for the lowest back pressure you can have if the outer wall is staying as persistent as possible. Now I'm gonna put the stuff to the flat and the curve lane, and then I'm gonna put you up on my screen and share the details. This is the flat line. The next extrusion move that comes is 70 cubic millimeters a second. And you can already see a major difference in the viscosity of the material that is coming out of the air. So this is flushing move at 70 cubes. Have a look at the material that is coming out of here. The diameter is in a reasonable range, and there is not a big difference in the way this piles up here. So this is way more thoroughly melted than the previous just straight line bores. Let me see how far I can extend that. So I just ran 90, that still worked, and now I can see all the things I saw with these just straight line approach at around 65-ish cubic millimeters of flow. That is what I can see here, starting with 90. Let's run 95. Yeah, now you can see all that pressure building up in that short Bowden tube up there. And it's still doing it, but you can see the viscosity has changed. But still, I just get some really minor under extrusion. That is just another hint how insanely good these LGX extruders are working. These are just pushing filament no matter what, and have a look at that tiny motor. It's running 0.75 amps only. That's just absurd. Alright, we're in the last lane, the curve. And what I think is pretty interesting is that we're only at 40 cubic millimeters a second, and I already start to see signs of this thing being overloaded. So the die swell is here again, the whole thing is kind of moving when extruding. Each time I have the camera in front of here, it's kind of an awkward setup, so it doesn't look as fluent as when I'm doing this alone. But you can already see how thick that line is. You see how big of a circle this already is extruded into? You can tell that it's thoroughly melted, and it doesn't make a difference if it's just the first few millimeters of an extrusion move where the material has stayed in the hot end for quite some seconds, or if it's continuous flow. This doesn't make a difference here, but this certainly does. So I guess we're already overloading this hot end. I'm gonna run the tests till the end and then gonna get you on the screen. So let's have a look together at the results of this, let's call it geometry check. So again, this is the part we've been testing. The first one is straight. This one is basically the same but drilled out. Then we got this flat section and then this curve section. And right here, I put all of them into a single graph. You can see here, green being straight, drilled, flat, curve. So it's basically 1, 2, 3, 4. I haven't done enough testing to use these values to compare it to different hot ends that are out there on the market. I can't give you a guarantee if some of these tests topped out at 50 or 60. I haven't used them or tested them in real world applications. That is another task. But I got all the information I wanted to have out of this test. I wanted to compare these in reference to each other. In all of these graphs here, I marked 2 points in the representation of the flow values. And this is what you can see here as load and skip. And load is essentially the point where I could see visually that something is changing. So basically the viscosity of the material has gone from something like this over to this, very wide lines that just behave differently. And I guess this is the point where we get in all sorts of trouble with layer adhesion in a real print. And you can see for the various geometry, it's all over the place. And then I marked where actually this extruder started skipping. So in this basic configuration where we're just using one lane, we should expect the 100 newtons of LGX pushing power. The Bowden coupling, or more the Bowden tube itself, couldn't handle the pressure and it's been ripped out of there. There is severe deformation of the PTFE tube, so I guess this is far exceeding what our usual load on a system like this should be. We want to be somewhere in a range where the extruder doesn't have to work that hard, then we're efficient. So starting off with the straight line, which is represented in green, we can see we managed to get somewhere in the 60 cube range where I could see the visible load. And then somewhere at 75 the extruder started skipping, and then it skipped real hard when I tried to do 80. The yellow line, which I drilled open, you can clearly see that there is a difference shifted to the left. And this is what I've been after, because this is very good news for all of us, because this means basically that it is totally appropriate to SLM print your hot ends, your internal geometries. And while for certain kinds of extrusion and molding, etc., the surface roughness of that process is just not working, for our filament-based extrusion, this is even an advantage. I mean, even if we take these measurements all with a very big grain of salt, it just shows that it's at least equal to that and maybe even on top. What that means is we have total design freeness in all of our geometries that are inside the hot end, and that is a very good thing. So now we can not only design straight lines and a few curves and bends and whatnot, we could totally do that in circles and whatever, you name it basically. And then lane 3 and 4, so basically flat and curve, are both designed to do a similar thing, and that is to get rid of the most outer layer that has already been molten and expose the fresh core to increase heat transfer to the core of the filament. Here we can see some very interesting and different results. So let's start with the curve section. And I could see right away from the very first flow test of 30 to 40 or whatever, there was a significant load on the system itself. Everything was a bit shaky and I don't know, you kind of just feel that the extruder was working way more than before. And that showed in it already skipping at like 65 cubes of filament flow. So this is clearly not the way we want to go. But then have a look at the flat section, and this is what gets me really, really excited, is that basically up to a certain point, the deviation here from the zero line is basically 1%. It could be well within my measurement setup here on the precision scale, or just be the compressing of the filament or some sort of effect in that extrusion. But the point that I specified as the load point is actually way past everything else, where every other hot end was already skipping. I could see those changes in die swell, in extrusion width, in viscosity of the extruded material. And basically even at 100 cubes it still kept going. With this kind of G-code, I wasn't even able to make the extruder skip. So what this tells me is that I cannot derive a definitive number off of this, but I can see that this is a significant improvement over all the other things. And with our approach of SLM printing our hot ends, it is no problem to integrate that into our melt channel geometry. Okay, well then, very shortly to my design methodology. So the very first tests you saw were just like my concept of this whole thing as an assembly group. So I wanted to know, is the cold end side, is it like drawing enough material out of here? Are these push style fittings working? Is the center to center distance from the heat breaks, is that all making sense? Do we have enough heating power? So that is solved with this guy. And then the next tests we did with the hot end comparison is basically how can we improve our flow channels down there to maximize the melting capacities of our system. And now comes the part, because this is basically all SLM printed in solid aluminum. Aluminum has the advantage of being dirt cheap in this process. You can expect very good surface qualities and you get a decent amount of heat transfer. And heat transfer is what we're going to focus on next. So heat transfer is measured in how many watts of power can be conducted per given area and per given temperature difference. And while aluminum sits there at around, let's say 220, copper, on the other hand, does offer up to 400. So it's more or less twice the amount of heat we can transfer into a given material. And that's why for the next test, we tried to use this copper tube to use it as an inliner for our aluminum SLM printed hot end, because copper SLM printing is a totally different thing and way more expensive. So if we could combine these two principles and insert this into something like this and basically double our heating capabilities, that would be a game changer. So let's see if we can make that happen. So you meet me at the lathe. I already chopped off 4 of these copper wires. These are 3mm OD, 2mm ID in the appropriate length, and I already put one in the collet chuck. I measured and cut the optimal length for these so that they perfectly sit in the hot end. I'm gonna machine them to the right length and also do the end work, so proper chamfering, etc. That is not too easy on these thin-walled tubing. Alright, so these are the tubings, 2 longer and a slightly shorter one. I just got 1 try to put them into here. This is my first test regarding the tolerances, if these fit in here. If they get stuck somewhere in the middle, I have no idea how to recover that. So I'm just gonna wing it, and usually I would nickel plate them because I know from my experience over the Minuteman hot end, even the slightest bit of moisture is introduced into these melting channels. These will oxidize and change the surface properties of the copper inside. So I contemplated and I thought I would just give it a try, because I have to change things either way and I don't want to get too involved in nickel plating now. I want to do that if I have my data, which shouldn't be a problem for extruding for a couple of minutes of material through here. So I put it back in the collet chuck because this is the best way to hold it without bending the tube. And now I'm going to try to insert the middle one, which is straight and therefore should be the easiest. So let's see. Okay, this one fits in here. Huh. So I didn't need that at all. Oh yeah, this does bottom out perfectly. But for the other two, I have to apply a lot more force, since I have to bend them while insertion. So let's see if that works. Already getting pretty tight here. So I've reduced the diameter of this copper tubing by 1/10 of a millimeter. Let me see if this fits now. At least it does extrude material. There are a few things happening. I don't really know what this is about. For example, the melt wanders off to the left and to the right. It may be to do with these channel above that are basically just reservoirs. So let me run the same tests as before and see where our limits are. I've already reached 70 cubes. Let's do 75 together. You can already see it skipping. There's just hot mess coming out of here. Skip, skip, skip. Okay. So I wasn't really expecting that. I would have guessed these numbers are higher, but we'll investigate why that is not the case. So you can see it started to taper off around 55, and I could see a visible difference in the viscosity of the material at that point, and then it skipped hard at 70 and 75 cubic millimeters. So it is basically on the low performing end of everything we have done so far. So usually physics is telling us what to do, and usually this copper material should have almost double the heat transfer to the filament, so why isn't doing that? It could be because of the missing surface treatment, it could be because there are two channels that are basically acting as a reservoir, and I don't know how they interact with each other. So let's do another test on a copper hot end, or something like a copper lining. That does involve these parts. So this is a sinking electrode out of EDM machines for drilling start holes. It is a very precise copper tube. Then I do have these SLM printed aluminum parts, which will be inserted here and here as connection points and soldered to that. And then we do have some nichrome wire to heat this up. So this is basically an attempt to make it as lightweight as possible. I'm just shooting here in different directions and seeing what I can hit with it. So let me just prototype this together. Okay, so I convinced myself that it is the better idea to just screw these together. So I have put in M4 on either end of this copper tubing and also an M4 internal thread into these guys. And these will screw on here. And then we got an M6 at either ends that we can use to screw a nozzle and a heat break into. So basically this is going to be our hot end, and since it wouldn't make any sense to use big heating cartridges and then we need to find some way to actually hold it onto here and make heat transfer. So I'm gonna try to use nichrome wire, which is essentially just a heating wire with a very known resistance, and this will get glowing hot if you apply a voltage to it. In this particular case I got some here on shelf. I'm using this 30 gauge wire, whatever that means in metrics. It is around 0.2 millimeters. And since I want to be having a load of somewhere around 50 watts of power at 24 volts, I can calculate that I need around 40 centimeters of that wire to get me in the ballpark area. And I can adjust voltage up and down to match my exact needs. So I'm gonna do a few things. I'm gonna wrap this in some kind of a insulating material, electrical wise, because we don't want to have short circuits over the coil I'm gonna be building here. So I'm gonna use Kapton tape. I think it will do fine for now, and then I'm gonna add a layer of another insulation that keeps the heat inside and also fixes this wire to the hot end. So let me prototype that together. So this is what I came up with for now. It is my duty to make sure that this is staying in place. What I got here. What I do now have is this here. I've used this many times in certain applications like this. So it's basically to seal in heat resistant in ovens and stuff like that. So welcome back. This is what I came up with. Again, E3D style cold end as well as heat break. And then you got the contraption you just saw me throwing together. So this is of course very fragile. I haven't tested yet if there are any short circuits. I figured I make a video about it now before it goes up in flames. So I'm gonna be very gentle with ramping up some heat in here. I'm gonna keep the camera on here and I'll show hopefully some extrusions. So we're at 60 degrees. If I give it another like 10 degrees, you can see the PWM signal pulsing here in that lead. So I'm gonna go 70. That wasn't enough to fully trigger it. I'm gonna do 100. Now it's gonna shut off and you can see it pulsing. I'm gonna type in 125 and have a look at the power draw. So it's right about 60 watts pulling. I'm sorry for the focusing here, but this is pretty hard. I don't have a manual focus on here. So we got some leaks, which are expected because I didn't put any PTFE stuff or something here on the threads. We just have to live with that, see how long it will work. The following extrusion is at 95 cubic millimeters. Skipping steps, throwing off the Bowden tube up there. There's a huge amount of back pressure, you can see it here, it's pushing out of these connections. So yeah, this is about the max it can do at 215 degrees, just like all the other tests. Alright, again here in the diagram, as you can see, I just added this copper line, which is orange in here. And basically what you can see, the three things to compare here is yellow, green and orange. I took the copper lined hot end out of the equation because I think this is just messing with our data. It is at the end a pure copper lined hot end and that should deliver different kinds of flows, but maybe it was thrown off because of these side reservoirs, etc. All that weird stuff is happening. But what we can take away here is that a drilled aluminum piece is skipping at 65 cubic millimeters a second. A SLM printed straight line of the same length is skipping at around 75, and a pure like drawn copper tube of high quality is skipping at 90 cubic millimeters. What I don't know at this minute is how much this is affected by the missing nickel plating. I know from the experience from my Minuteman hot end that it did make a big difference, but just in long-term use. I didn't thought that for the initial just testing this would make a difference, but maybe it does. So let's just derive ballpark numbers from here. So what I can take away from here is that the SLM printed aluminum version is looking really, really interesting because we have all the design freeness in the world. We can just go ahead, build the weirdest channel geometries whatsoever, and basically you get almost finished parts from any manufacturer home. You don't have to do copper tube bending, you don't have to do nickel plating whatsoever. You just retap threads and you're good to go. Alright, so let's try to wrap up a few things here. So this is pretty much my first shot at the hot end that I want to make open source for all of you guys out there. It is designed for people and enthusiasts like I am that want to just push limits of 3D printing, and if flow has become one of your main issues and you just can't find anything on the shelf that fits your needs, maybe this is for you. The other big category would of course someone be that makes money with 3D printing, and let's say you have a big ass 3D printer that is running off of filament and not pellets. You may run into the issue that you have very large build volumes and therefore layer times, but just the extruder or hot end assembly is your limiting factor. And if you can double your flow, you can pretty much double your profit off of your products you 3D print. And this is where I'm aiming with that. I think it will probably somewhere in the neighborhood of this. All the other stuff we did today is just to find out about perfect geometries and materials and whatnot. You have been here with me all the time. So there is a huge list of things I want to improve for the next version where we're actually going to print with it. But I need your guys' input here. So let me know either in the comments or on my Discord or my Patreon site, what is it that you guys want to have in here and what is the most important part for you. So right now, this whole contraption is about 125 millimeters long, including the push style fittings and the nozzle. And just the hot end itself is 130 grams, including like heat break, etc. If you count in the whole thing with cables and heat cartridges, that's another 30 gram on top. And if you add in a direct drive extruder, just like this one, we're gonna add another 420. So in summary, this comes down to 585 for this complete package. That being said, I am pretty sure that I can get rid of at least another 30 to 40 grams on this setup, especially in the cold end department. There is a lot of things to spare, but then again we have to talk about fans and ducts and etc. But you know the deal. Anything you type me on these various channels will be in some way or the other included in a more or less final product. All of these parts will be downloadable. You will get a bill of materials, so like links to these push style fittings, to these heat breaks, to screws and nozzles, whatnot. And yeah, the SLM printed parts, you can basically just download STL or maybe step files and just send them off to your local or online manufacturer. Okay, addressing the elephant in the room, which is this guy here. So this project started a few months ago actually, when I was like designing the first iterations of these guys, and I said, hey, I do need some kind of an extruder setup to make it happen anyways, but I don't have the time to make that happen all by myself. And as of right now, you can see what kind of a monster I've built beforehand to make that happen. But this comes with a lot of downsides. So talking about weight, talking about how to drive them properly, you either need some very janky wiring or you need 4 slots on your 3D printer main board. Then it's just a thing of maintenance. There are so many parts on here, so eventually something is going to break. We need to get down on maintenance and order of parts, etc. That will make this whole system more reliable and usable for everyone. So I reached out to Bondtech and said, hey, you arguably have the greatest extruder on the market. The LGX ones have been just working like a charm from minute one. And I proposed the idea of just making a modular version out of it. So you basically take your large gears and stack them on top of each other just with a different housing in it. And they said, fuck yeah, let's do it. And this is basically what I'm holding in my hands here. This is still a prototype, so Bondtech insisted that I keep telling you that. This is first generation. The interesting thing is, this worked right out of the box. I just plugged it in, got my values in the Clipper software, loaded 4 types of filaments, and it is working like a charm. And no matter if I do 1 or 2 or 3 or 4, it just works. And the combination of these two things actually set us in a very sweet spot for 3D printing. Because have a look at that tiny motor up there. I was just driving that with 0.5 amps. The guys over at Bondtech said that in this configuration the extruder will do 25 newtons pulling force per channel. And if you ask me, anyone that uses more pulling torque on their extruder is not running it at the right speeds. There is a point you can push your hot end for, like in this configuration at 215 degrees, I can push for 180 cubic millimeters. It will do it. But you can see that the forces are just going through the roof. By running your extruder/hot end combination at a lower working point makes so many things so much easier. It gets rid of all the stress in the system, and it's basically just flowing with the least amount of force needed, and therefore I can pretty much use this tiny motor to pretty much melt 1 kilogram of material per hour in this configuration, and it doesn't even sweat with it. So for the future, this will be open source. This is a product. So I guess at some point you can buy something like this off of the Bondtech website. I haven't got any idea about pricing whatsoever. That is just their deal. If you're someone that actually earns money with 3D printing, you don't want to do tinkering with all sorts of funny stuff. You want to have a reliable system that just works. And I think this is the perfect opportunity to buy something like this if you can afford it and if it makes sense for you. And we're planning to do a sophisticated connection between these two, either in a direct drive situation or a Bowden setup, just like you saw me on the test stand. But of course, the whole thing is also designed so you can pretty much hook up anything aftermarket on here. It is not designed to work specifically with the Bondtech, but it is designed to specifically work good with it. But you can pretty much buy 4 of the cheapest extruders out there on the market, just plug them in any sort of configuration, and you're off to the races. So now, I think it is time to wrap all of this up. I've done the first steps. I have a solid list of things I want to improve here, but I'm waiting for you guys in the comments or on my Patreon site. Thank you so much, all of you people. Come join my Discord. There will be the most active discussion, I think. I try to include everything you say that is possible, because I want to make it the Hotend of the community. So therefore, I'm really eager to know what you guys are thinking about it. Throw everything in the comments. So I hope you learned something. I hope you're just as hyped as I am about this. My name is Jan, and I build stuff so you don't have to. See you next time. Bye.